Hello everyone, this is Dr. Webb, and in this video we're going to start talking about related rates, or what are called related rates problems. And so I thought it'd be good to start this off, start off going through this, using an example. And so this equation right here is an example of what's called a Cobbs-Douglas production function. These pop up in economics. So the origin of this is from the first third of the 1900s, around 1930 or so. Douglas was an economist. He did a lot of studying of countries and looking at how much of their economy was dedicated to labor and how much was dedicated to capital, and then trying to connect that to the total production of the company. And he took the data to a mathematician whose name was Cobbs, and together they came up with this basic type of formula for how to do it. So in a regular Cobbs-Douglas production function, the P is production, the L is labor, the K represents capital, the 2 and then the exponents there, that I put those in myself. There's a more general form of a Cobbs-Douglas production function, but I put in these values so we can start playing around with it. Okay. So let's suppose we have some country, and this is the Cobbs-Douglas production function for it. Well, if we knew that, let's say that all of this is in trillions of dollars, which makes sense for large countries. So let's say that L equals 11, so that's sort of representing $11 trillion is being spent on labor. K equals 8, so that's sort of saying $8 trillion is being spent on capital. So capital here means, materials, factories, anything that's really not labor. Well, then using this formula, we can figure out what the production is, right? And it's pretty much just plugging things in. 11 goes in for L, 8 goes in for P. We plug this into our calculator. Spits out 20.3. And so that would be saying the total production is $20.3 trillion. Okay. And so that's what we just figured out before. And so, this is a calculus class. Calculus is really about looking at what happens when things change. So if we go a little bit deeper and say, well, what if we also knew the rates, that we knew the values of labor and capital, but we also knew at what rate they were changing? Could we then use this formula to figure out how the production is changing as well? Okay. And so the deep idea to get on how to do this is that if we're thinking about L, labor and capital and production, L, K, and P changing, well, if they're changing with time, well, that means that we can actually think about them all as functions of time, right? If they change with time, then they are functions of time. And so for labor, let's say we said before that $11 trillion is being spent on labor, but let's say that spending is going to decrease at a rate of $1.2 trillion per year. Okay. So this is sort of the value. The $11 trillion is the value of labor right now. And then there's a change. The rate of change in the amount spent of labor it's decreasing at $1.2 trillion. So how can we write that sort of in terms of functions? Well, the $11 trillion spent on labor, that's saying the value of the function is 11. The decrease in the rate of $1.2 trillion per year, well, that's talking about a rate of change, and so that's talking about the first derivative. And so we can set the first derivative here to be minus 1.2. And so the minus sign there is talking about the decrease. Okay, what about for capital? So if we say that currently $8 trillion is being spent on capital, and it's decreasing at a rate of $500 billion per year. Well, the $8 trillion being spent on capital, that's telling us the value of the function. The decreasing at a rate of $500 billion per year, that's a rate, so that's telling us about the derivative. Okay. And so now we go back to original formula, and we want to know about how P of t is changing. Well, we have this equation here, so how do we get the derivative of P of t? Well, we're going to take the derivative of the whole formula. Okay. So on the left-hand side, it's just P of t, so if we take the derivative of P of t, we're going to get the derivative of P of t. So that's simple enough. On the right-hand side, we've got 2 times L of t to the 0.75 times K of t to the 0.25. Taking the derivative of that is going to take a bit more work. Okay, so we're going to focus right now on taking the derivative of the right-hand side in terms of t. Remember, we're just treating this L and t as functions. When we get the derivative, we're just going to call the derivative L prime of t and K prime of t. Okay, so if we're looking at this, the 2 is a constant, so we can pull that out. And then as we're looking at the structure of this, well, I've got L of t to the 0.75 getting multiplied to K of t to the 0.25. Right, so I've got 2 things multiplying together, and so that's telling me we should use the product rule. Right, where we can think about this as being the L to the 0.75 being F and K to the 0.25 being G. And then when we take the derivative of that, that's going to be F prime G plus FG prime. Okay, so our F function here is L of t to the 0.75. Our G is K of t to the 0.25. Okay. So when we're thinking about taking derivatives of both of these, we have L of t is then being raised to the 0.75 power. So we're going to think about this for this part right here using the chain rule, where my outside function is going to be, let's use t because that's the variable we're using. So it's t being raised to the 0.75 power. The inside function is L of t. Okay. Power rule here, it's just t to the power is 0.75, so the 0.75 comes down. And then we're being multiplied by t to the 0.75 minus 1 is going to be minus 0.25. On the other hand, derivative of L of t is just L prime. Okay, so we're going to plug these in. So chain rule is derivative of the outside with the inside plugged in. So then it's going to be L of t to the minus 0.25. Okay, we got to do something similar for K of t to the 0.25. So here, the outside function is t to the 0.25. Inside is K of t. Derivative of the outside, the 0.25 comes down. T and then 0.25 minus 1 is going to give me minus 0.75. Derivative of the inside here is just K prime. So G prime, it's going to be the derivative of the outside with the inside plugged in times K prime of t. So putting this all together here, now I've got my F, F prime, G, and G prime. So we can go back and apply the product rule. So applying the product rule here, we pulled the 2 out, and then we have F prime G. So it's going to be 0.75. Oh, I forgot to multiply in the L prime there. 0.75 times L of t to the minus 0.25 L prime of t times k of t to the 0.25, and then we need to add fg prime, so that's L of t to the 0.75 times g prime, which is 0.25 there, k of t to the minus 0.75 k prime of t. At this point, this work is getting mighty messy, so it would be nice if I could just wave a magic wand and make it look pretty. Oh, there it is. Distributed the 2 between these. So that was everything that was written before, but a lot nicer looking. And then if we notice, we've got some negative exponents here, but this is negative 0.25, and then we have positive 0.25 right there. From the other term, we have positive 0.75 and then negative 0.75. So we actually can combine these, at least to make it look, you know, perhaps visually a little bit more exciting. And we can rewrite it to look like that. Okay, and so here's the derivative that we're going to use. Okay. And so if you notice in this derivative, we still have the labor function, the capital function, and the derivative of labor and the derivative of capital are all in there at once. Okay. So putting together the left-hand side and the right-hand side from what we had before, we have taken the derivative of our formula. This is what we get. Okay, recall beginning we said that labor was $11 trillion and was changing at, decreasing at $1.2 trillion per year. Capital was $8 trillion and decreasing at $500 billion per year. And so we can just go and start sticking these in. Where we need them to go. And let's make this look nice. So there's P prime, everything plugged in. Oh, I've got color coding. All my L of t's there. My L prime sitting right there. My K of t's sitting there. And finally K prime getting plugged in there. So everything lines up. We plug it in and we get minus 1.98. So just a little bit more than minus 2. So what exactly does this mean? So remember, production was in trillions of dollars. These derivatives are in trillions of dollars per year. And so at the end of the day, the units for this is in trillion dollars per year. So what does this mean? It means that the production is decreasing at a rate of $1.8 trillion per year. Right? So if there was some big shock to, say the amount of it's being spent on labor and capital, like say there was a pandemic going on, so there was a drastic decrease in both labor and capital, then this is what you might see happening to production. right? And so if you think, when you think about this in terms of percentage rate of change, this actually means it's almost a 10% decrease. Okay. So this whole example that we just went through, that's an example of what's called a related rates problem. Okay, so what exactly do we mean by this? So strategy, how to do a related rates problem. So usually related rates problems, it's everything evolves around some formula relating quantities. These quantities, you consider them functions of time, and then you want to find out about how one of them is changing if you know information about the other ones, right? So you have to start off with some kind of formula, some sort of equation relating them, and so this is the Cobbs-Douglas equation that we were using. Then you want to take the derivative of that formula, treating all of the quantities, at least all the quantities that change, as being functions of t. If a quantity doesn't change, then you can treat it like a constant. And so this is the derivative we got. And then the last step is to plug in the quantities and the rates. So plug in the values of the function and values of the derivatives, which were given in the problem, and solve for what you want. Okay, so I know this is an awful lot to go through at once. I'm going to be doing another video doing some more examples on this for the beginning of next week. But this was just to give you a taste of this right now. So as a sort of a starter practice problem on this, we're going to say Old MacDonald has a farm that's a rectangular field that's 1,000 feet east to west and 1,500 feet north to south. But then the sides of this field are changing. So on the one hand, on the eastern edge of the field, this probably would help to draw a picture of this. Let me see if I can draw you a rough picture. So east to west is 1,000, north to south is 1,500. So it looks roughly like that. 1,000. And then this is 1,500. And then this is saying that the eastern edge is decreasing at 2 feet per year. On the northern edge, shifting course, and that's actually enlarging everything by 1 foot per year. Okay. So I want you to go through and walk through figuring out how this is affecting the area. At what rate is the area changing per year? Okay, so the first step, we're going to go through the same steps that we did for the Cobbs-Douglas equation. So the first step is just find a formula relating area to length and width. Right, so given length and width of a rectangle, how do you find the area? That's the formula we're using here. Okay, then once you have that formula, take the derivative of it, treating area, length, and width all as being functions of t. So like if L of t, this is our length, when you have to take the derivative of it, just call its derivative L prime of t, etc. Okay. And then last, once you have this derivative, then plug in the values that are given to you, the 1,000 feet, 1,500 feet, decreasing by 2 feet, increasing by 1 feet. Plug them in to the appropriate places and use that to figure out how the area is changing. Okay. So we will talk about this Friday morning, and we'll go back through how to do this, and then over the weekend I'll put up another video that goes through some more examples of doing this. Okay, so hope to see you soon. Bye.